Hello everyone, my name is Oster Movinsky and I'm an assistant professor at New York University. This is the third lecture in my mini course on physical design databases, and this lecture will focus on the Liberty, LEF, and DEF formats. Now that we've discussed taxonomy and the precise naming of circuit components, we can discuss how all of these components are represented in real software. For those who have taken a course in databases, you likely already know that there are different ways to format a database, particularly when storing the database on disk versus storing the database in main memory. Fortunately for us, there are a few broadly used file format standards for storing circuit information on disk. The most important ones for our purposes are Liberty, LEF, and DEF. These standards not only are compatible with OpenDB, but they're also compatible with many proprietary tools as well. These files get parsed and loaded into OpenDB, which will form the memory database that gets used for all of the EDA stuff that we're going to discuss later. First, it's important to talk about these standard file formats because their data organization serves as the foundation for the databases of OpenRoad. We need to understand what information they contain, how they format their data, and how this data will be used in OpenDB. Therefore, these file formats will be the focus for the rest of this lecture. One of the first questions to ask is, why are there three file formats? Liberty, LEF, and DEF exist because they contain different types of information. There also is a little bit of history behind the formats. The Liberty format was originally created by the EDA company Synopsys, whereas LEF and DEF formats were originally created by the EDA company Cadence. Each format was created to fulfill an unmet need in the EDA ecosystem at the time. The important thing about each of these formats is that the standards were open so that anyone could use them. This meant that for developers, they could use an already developed standard rather than trying to create their own from scratch. And this also ensured that the formats were interoperable with any EDA tool that tried to use them. Thus, the standards have been widely adopted, even if there might be a little bit of overlap between the formats. As for the types of information, the Liberty format is primarily concerned with storing the logical and timing characteristics of master cells. Additionally, it can express how much time it takes for a signal to propagate through that cell, from the input to the output. An example might be that when the input transitions from 0 to 1, it takes 0.27 nanoseconds for the output to transition and stabilize. It may also identify that different transitions take different amounts of time. For example, if the input transitions from a 1 to a 0, the delay through the cell is instead slightly slower at 0.32 nanoseconds. Here, LEF and DEF stand for Library Exchange Format and Design Exchange Format, respectively. Whereas Liberty is concerned much more with the logical information, these formats are concerned with the physical geometries of the objects, including masters, nets, and blocks. These formats store what are the actual shapes and sizes of objects if they were laid out in a physical chip. Nothing in the Liberty format, with maybe a couple of exceptions, is actually concerned with the physical shapes of the master or the circuit. That's where LEF and DEF come in. Next, I'll talk about each of these formats in more detail, but I should also take a moment to note that other formats exist too. Some of them are proprietary, so they can't be used in open source software, and some contain other information like detailed parasitics, spice modeling, etc., which aren't important because they are beyond the scope of this course. Next, I'll talk about how each of these formats in more detail, but I should also take a moment to note that other formats exist too. Some of them are proprietary, and so they can't be used with open source software, but also some of them contain information like detailed parasitics, spice modeling, etc., which aren't important because they're beyond the scope of this course. So, Liberty. The Liberty timing model was created by the EDA company Synopsys and then open sourced for the wider EDA community to use. It's not easy to put a date on exactly when this happened, but the earliest evidence that I found was a user manual from 1998, along with some indicators that it may have been in development since the early 90s. Synopsys was the most dominant player in circuit synthesis, so their Liberty format eventually worked out to be the standard solution for logical circuit data. The format has been updated many times since then to account for newer technology constraints and challenges, and it's still the dominant standard today. Liberty is often shortened as lib, especially since .lib is the standard file extension. For those of you who have worked it with proprietary tools before, you may have also seen some other file types based off the Liberty standard, such as .db. Liberty is also a plain text format, meaning that you can simply open the .lib file in a text editor and read the details. The syntax is a little bit similar to the JSON format, if you've ever seen it, except that Liberty actually predates JSON. Let's take a quick look at an example of some important features that show up in a Liberty file. This example is taken from the NAND 45nm cell library. So this library is a collection of masters which belong to a non-fabricable 45nm process, meaning that you can't actually manufacture it, but it's a synthetic version that's been created which helps model what a real 45nm process might look like. So this library will include cells such as inverters, AND gates, OR gates, XORs, that's exclusive OR, NAND gates, NOR gates, etc. For all types of major devices that you may want to include. The info is provided at a specific characterization point, which means that it's a specific voltage and temperature. For example, this one is provided at 25 degrees Celsius and 1.1 volts for the supply voltage. For those of you who have a circuit background, you may note that the characteristics of a circuit, for example, the timing information, the power, is greatly affected by both the temperature and the supply voltage. So for that reason, the Liberty file is provided at a specific characterization point. So here is the first part of how a Liberty file actually looks like. For this instance, we can see that this is sort of the header of the file, where it dictates what are the units being used, what are the important parts, and how are the quantities quantified. So we have the time unit, in this case it's in nanoseconds. We have the leakage power unit, which is one of the primary types of power used in here, and it's in nanowatts. We have voltage, which is volts, the current unit, which is in milliamps, the resistance unit, which is going to be in kiloohms, and then the capacitance unit, which is in femtofarads. You may know a slightly different syntax here, but the distinction is not super important. The next part of the file is going to talk about the operating points. So as I just mentioned, we have our nominal temperature, which is 25 degrees Celsius, and we have our nominal voltage, which is 1.1 volts. After that, we have our cell definition. Note here that Liberty is not using the same syntax taxonomy that we talked about in lecture 2. So here it's going to use some different terms which I may have explicitly said not to use, and it's a little bit unfortunate that there's a difference. But the reason for this is because Liberty is separate from LEF and DEF, and they're both trying to represent separate parts of the sort of circuit spectrum, circuit taxonomy. So here we have a statement that's called a cell, but in OpenDB terms, this will get translated to a master. So in that case, we have a master inv x1, so this is a x1 strength inverter, and then we can first see what are the power terminal definitions. So these are going to be some of your B terms for your power that are declared here. We have a PG pin VDD, so VDD is a very common name for your power supply. In that case, we have the voltage name VDD, and it's a primary power. Then we also have the PG pin VSS. This is a very common name for the ground that's used to connect to a circuit. So in this case, the voltage name VSS, and it's the primary ground. Next up, we have the pins that are inside of the cell. So those are Liberty terms. In our OpenDB terms, these actually map to the terminals that we just talked about. In this case, we before talked about the power terminals. Now we're talking about the signal terminals. So these are going to be your normal inputs and outputs for your gate that you consider when you're looking at a logical view. In this case, we have the direction that's listed. It could be an input or it could be an output. and then we have the capacitance that's associated with that pin. So there's a little bit of electrical capacitance for the gate for whatever the connection is on your master, and this will be documented here. Next, we have also the output pin. So if we had the input pin for the inverter, in this case it's the output. We can see also that there is a max capacitance here, and then there's also a function annotated onto it. So in this case, the function is written out as a Boolean expression of not A. Next, we have the timing information for this output terminal. Here we have a property called cell fall, which represents the delay of the master. This delay is specific to the case where the output is transitioning from a 1 to a 0. Next, you see a whole bunch of numbers. We don't really need to go into too much detail about how this works, but just understand that this is essentially a lookup table to determine what the delay actually is. You have an index 1 and an index 2, and these indices are used to look up the delay in the big table of values. Recall that the time unit was defined in nanoseconds, so the values in this table range from 0.003 nanoseconds in the top left to 0.15 nanoseconds in the bottom right. Next up in the timing block, we also have cell rise, the rise transition, fall transition, and each of these properties looks exactly the same as what you just saw for the cell fall property. There's going to be a bunch of values that are used for a lookup table to determine these important timing characteristics. So there are going to be the delays for the cells, both when the output is rising or when it's falling. And then there's also the transitions. So it's not just the delay from input to output, but the output itself, how long does it go from high to low, or how long does it take to go from low to high? We also have the internal power up next. So we have fall power, rise power, very similar notions. And also these are based off of lookup tables, which will do the same thing as time, but for power instead. One thing to note is that also the cell rise and cell fall, those are going to be the liberty terms. These are, sort of indicating what is it for the master, or rather an instance of that master. Next, we have some power statements specifically for the leakage power. So this is a specific type of power which is drawn when your master isn't actually doing anything. It's not transitioning from one state to another or transitioning the outputs. So there's a when and a value property. The when is going to be a Boolean expression. In this case, the first one is not A, and the second one is the opposite, A. So it tells you whatever state of A is, it can give you a value for either one of those. And then the value is either 10 or 18. And remember that we also defined what is the leakage power unit, and that was going to be in nanowatts. So for the value of the leakage power when not A is true, meaning that when the output is 0, it's going to be leaking 10 nanowatts of power. And when it is true, when the output is high, it's actually going to be leaking 18.6 nanowatts of power. And then lastly, at the bottom, you'll see, well, there's this other thing called cell leakage power, and that one's 14. This is the case where sometimes you don't actually know what the current state is, but you want a decent approximation. So here it's going to be defined as 14, which you'll notice is just the average of the two values that were given. So for further details on Liberty, it's a very, very verbose format. I tried to cover some of the most important details here, but you can also search for the Liberty Reference Manual online in order to find the full specification. And if there are any parts of the spec or the file format that you need to know, you can find more details there. You can also look at the full NAND 45 Liberty file online, either in the Open Road repository or elsewhere. Next, we're going to look at the Library Exchange Format, or LEF. It was created in the early 1990s, possibly late 80s actually, by a company that eventually became part of Cadence. Similarly here, LEF, along with DEF, became the industry standard format for physical information in circuits. It's been updated since then, and it's still the de facto standard. Even though LEF is a single format, The way that it's used is often divided into two separate use cases. One is usually what's called the library LEF, which has all of the physical geometry and size information related to the master cells. And then the other is what's called the technology LEF, which enumerates all of the rules about how the physical metal wires are allowed to be drawn on the chip. While one could include both of these classes of information on just one LEF file, generally they're separated into two LEF files. This is because of a few reasons, but a leading reason is that the technology LEF information could be used along with multiple different libraries. LEF uses the .lef extension and is also a plain text format, so you can just open it up and read it with the text editor. Let's look at an example of some important features that show up in a library LEF file. So this example is taken again from the NAND 45 nanometer cell library, and it has the same list of master cells, but one important difference to note is that LEF does not have a characterization point. The way that you draw the master doesn't depend on operating conditions, so it's not really necessary to specify anything like that. In the library LEF, there isn't much preamble to it. Most of that is in the tech LEF. Here we have the macro inv_x1. Again, macro in this context is a LEF syntax, but it's going to be master in OpenDB. In Liberty we had cell, here we have macro, but in OpenDB we have master. So we have down here the class property, which identifies where and how this master is supposed to be used. This inverter's class is core, meaning it can be placed anywhere in the normal place that a gate can be placed, but there are several other classes that can be defined for different purposes. For example, a master, which might only be used for off-chip connections, might have a separate class identified. There's also one for masters which are only used to fill empty spaces in your chip, and so on. So if you look at the LEFDEF manual, there's a full list of descriptions for each of these classes and what they're supposed to be used for. Next, there's an origin property. You can think of this as the anchor or reference point to the master. Just like when you draw a graph, you have to choose an origin point. For many graphs, this point is located at 0, 0, and the same is true here. Unfortunately, the origin sometimes isn't 0, 0, which means as an EDA developer, you will have to account for that and explicitly check when the origin is something rather than just assuming it's 0, 0. Next, there's a symmetry property, which identifies how this master can be flipped or rotated when placing it as an instance in the chip layout. So here, XY means that this cell can be mirrored over the x-axis or over the y-axis. And it also means that it does not have the R90 property, so it cannot be rotated 90 degrees. There's also the cell site property, which I'll discuss a little bit more in the technology LEF. And then lastly, there's a size property, which is measured in x by y microns, or micrometers. So here, the cell size is going to be 0.38 microns by 1.4 microns. You can multiply them to get the area, which is not explicitly stored here, and the area would be 0.532 square microns. Next, we have the A terminal definition. Again, the keyword in LEF here is called pin, but this is semantically equivalent to a terminal in OpenDB. The terminal is identified as an input, and then it has a few properties related to the antenna rules and antenna checking, which may be briefly covered in a later lecture. Next, we have the master pin definition. In the LEF, this is the port keyword. This pin is drawn on layer metal 1, which represents the first metal layer, and then the exact geometry is specified by a rect statement, which is a pair of XY coordinates used to form a rectangle. The terminal for ZN looks much the same as A, so I'll skip that, but then we also have the terminal definition for the VDD terminal. Here we can see that this is a power supply pin by the use power property. So in this case, the direction is marked as an in-out rather than specifically an input or an output. This is by convention because the power draw of an instance can affect the whole rest of the power network, so it doesn't really have a defined direction like the way a digital signal pin does. There's also a shape abutment property, which sort of has to do with how the instance is connected to other instances around it. Typically, multiple instances are going to be placed right next to each other. And so instead of having to route a specific connection between this pin and another pin, it says that it can just simply touch each other by abutment. And the reason why this is useful is because it can tell your EDA tool that it doesn't need to do the extra effort to route it. So that's a convenient way to let your tool know that. Lastly, there is the master's pin, which is again on metal 1, but this time it's composed of 2 rectangles. For the LEF technology example, this is again coming from the 45 nanometer library, and the rules are tied only to the underlying 45 nanometer technology, not a specific library of masters. So we covered a LEF library. You can imagine that there's a different LEF library which is also tied to this set of rules. In the TechLEF file, we start with a few header properties. One of the first ones is the database unit, but in order to explain database units, or DBUs, I first need to explain database math. Sometimes, when one wants to represent a fractional value, the first instinct in software is to use a floating point type, such as a float or a double. The problem with these types is that they are approximate and can accumulate errors as you do more and more operations with them. But for these circuits, we generally have a minimum resolution that we care about, say maybe 1 nanometer. In that case, we can give up the arbitrary precision of a floating point type and instead use an integral type, which isn't approximate and won't accumulate errors. The key thing is that you need to do a scaling factor to convert your integer to the represented fractional value. So in this example, this integer is what we call in database units, or DBU. And it can be converted to microns by dividing it by the scaling factor given in this data type. In this example, the scale factor is 2000, which means that every dBu is going to be 1/2000th of a micron, or 0.5 nanometers. So this is essentially a way of reflecting that for this technology, there is nothing that requires more than a precision of 0.5 nanometers. This simplification is so important that EDA tools encoded it here in this LEF format to recognize this. One thing to note is that you can't have an arbitrary scale factor. The LEF specification dictates that it has to be one of 100, 200, 1000, 2000, 10,000, or 20,000. And so this corresponds to a range of 10 microns at the largest to 50 picometers at the smallest. Next, there's a manufacturing grid property. In a very similar manner, the manufacturing grid sets the minimum resolution that a designer is allowed to draw any polygons for the process. This value is in microns, so 0.005 microns here is equal to 5 nanometers. This means that you're allowed to create a grid on your chip where if every line was 5 nanometers apart, any point of the polygon that you draw must be aligned to this grid. The reason for this is not only to simplify implementations for EDA tools, but also to represent the precision limitations of the manufacturing process. In this 45 nanometer technology, the foundry is likely not capable of creating features on the chip which have a precision of less than or greater than 5 nanometer increments, hence the requirement that all points must lie on the nearest 5 nanometer interval. Lastly, there is a structure called a site. The best way to imagine this is that each instance of a master is like a Lego brick, and then you're trying to place that Lego brick on a placemat. Each bump on this placemat has a certain pitch in both the x-axis and the y-axis. Then you can place the Lego bricks on that placemat as long as they are on each of the bumps, and it has the right bump size. Additionally, the brick can be any size as long as the width and the height are a multiple of that bump pitch. So that's the same concept as a cell site in LEF. This cell site defines the X pitch and Y pitch, and in order to fit properly, it requires all masters to be multiple of this rectangle. This site is also required to have a name because there's no reason why you can't have another cell site with different dimensions, which is the basis for a different library of masters. Next, we have the preferred direction of the layer. This relates to a concept called Manhattan routing, where each layer is routed in alternating directions. For example, metal 1 is going to be horizontal, and then metal 2 is going to be vertical. Then metal 3 is again going to be horizontal, and so on. The reason for this is that it helps to maximize the number of available routes without having to zigzag. Instead, to change directions, you can go up one layer or down one layer to route in the opposite direction. So in this case, the LEF file will directly specify which direction the metals are preferred to be drawn in. In advanced processes, this can actually be a very important constraint because sometimes drawing in the non-preferred direction is forbidden. In that case, you wouldn't be able to draw a vertical wire on metal 1. You would have to connect to metal 2 first with a via, and then route in that direction, then route back down to metal 1. Lastly, we have the example of a via layer, which is also called a cut layer. So these represent layers where vertical connections are made between routing layers. So here, for example, via 1 is going to connect between our metal 1 and then our metal 2. And it's going to identify the region where this via is located, how big the spacing has to be, what's the width, etc. Many of the same constraints that you saw for metal 1. Next, we have the design exchange format, or DEF. This is defined in the same standard as LEF, so it's literally the same manual if you go to look it up online. And similarly, this is an industry standard format for the instance placement information, as well as wires and net connectivity. So in the LEF format, we had all the sort of general information for the process. We had information about the masters, and then now DEF is going to tell you sort of actually how are all of those used. Sort of what is in your design, what are the actual instances rather than just the modules, just the masters, and how are they placed and how are they connected. In this case, the file format is going to be in the .def file extension, and then again this is a plain text format, so you can just open this up and then read it in plain text. This example is again going to be the same 45 nanometer library, and then this design that we're looking at will be actually the same example design that we looked at in lecture 2. And then this design notably is going to be after placement and routing. So the DEF format can actually represent different stages of your design. And so maybe at some points it might not be placed, it might be placed, it might not be routed, it might be routed. We're going to look at it sort of after everything is already in there and you have the maximum amount of information. So here we have an example from the header of the DEF file. First thing to note is that there's a design with a name. In this case, the name is top, so that matches the example we had in lecture 2. Next is we have a similar notion to database units. This case is 2000, and that should hopefully match what's in the LEF file, but it doesn't necessarily always, so that's something to look out for. But the tools should hopefully be taking care of this for you. Then we have a die area statement. So this is a rectangle that's specified as the lower left coordinate and then the upper right coordinate. And so in this case, it's 0, 0 to 70,000, 70,000, and those are going to be in dBu. So you divide each of those by 2,000 to get the corresponding value in microns. Next is going to be a bunch of row statements. So we just talked about cell sites, which are sort of those individual bumps on your Lego, and then rows are going to be strings of them together, next to each other one by one. So these row statements just simply specify one row at a time, all of the rows in the design. So for example, row 0, it's going to specify where it is, where the sort of start point is, and then it's going to specify how many of those individual cell sites are within a row and grouped together. Then there's going to be row 1, row 2, and it can go so on for however many rows there are in your design. And so all of these cell sites, sort of, all of the X cell sites and Y cell sites will specify all of the placeable sites for each of your instances in your design. So this is just sort of creating a grid of all of the places where you can sort of snap on your Legos, or rather place your cells. Here we have tracks. So we'll talk about this a little bit more later on, but the idea of a track is just how I mentioned that we want to sort of have a minimum pitch of the metals that we use, and this is going to specify exactly how all of those metal lines are laid out if you were to draw a route that goes through there. So there's tracks in X, tracks in Y, and this is useful for later on when you do the routing of from one instance to another instance. Next, we have a via statement. So this is going to be the vias that are actually used in the design. There's a lot of info here. The main thing is just that there's sort of a template that's used. Usually this is specified somewhere in the technology LEF, and it's going to tell you exactly which metal layers it's connecting, what are some of the spacing constraints on it, if there's an array of these, how many are in the array and what is their spacing and things like that. Next, we have components, and the components are literally what are the instances that are used in the design. Also, where are they placed? So here we can see inst1, that was the name of our AND gate instance, and then inst2, that was the name of our inverter gate instance. We can see that they have been placed, and the specific location that they've been placed is given by those coordinates. And those are the coordinates of the origin of that cell. So remember, we talked about the origin in LEF, and that's usually at 0, 0. So that's talking probably where is the bottom left corner placed of that instance. And then the last little symbology at the end there, N or FS, those are sort of keywords that denote the orientation. And you can look up what are the orientations in the LEF-DEF manual. The next section that we have is the pins section. So in this case, this is going to represent the block terminals and block pins of the design. So here you can see that at each of the dashes is one of the block terminals. So we have in1, in2, and out represented here. We also have the nets that they're connected to. Just as we mentioned before, we typically like to have the block terminal the same name as the net that's connected to it. And so fortunately here that's the case. And then it also specifies what is the direction of it, as well as whether it's a signal, what type of connection it is, and what are all of the individual metal objects here. So you can see that there's the layer that's specified, you can see that there's the shapes that are specified, the coordinates for each of the rectangles that make these up, and so on. Next, we have the second to last section, which is the special nets section. Special nets is simply a way of stating that there are some certain nets that have to be handled in a special manner. Most of the time, it's just going to be the power nets that are in here. And the reason why these are different is because typically you're going to form either a grid or some other kind of format or shape rather than the point-to-point connection that shows up in a lot of other places. So normally you want to connect your power and ground everywhere in your chip, and it's going to have a different type of routing than the routing that's used for individual instances on their signal connections. So here we have our in1 net, and that net is going to be connected to the pin in1, and then also connected to the A1 pin of inst1. It's going to be a signal type, and then it's going to have a bunch of metal routes in between them. So a little bit of syntax here to note is that you may see some asterisks or stars here, and that's a special way of noting that that coordinate matches the previous coordinate that was specified. So if, for example, you have a star in the y value, that means that that y value was the same as the previous y value. And that's just to sort of save a little bit of space when specifying things. This is super useful because normally these routes are rectilinear, meaning they're only going to go across or they're only going to go up, but they won't usually go at sort of diagonal angles. And so that's a useful way of specifying that. You can also see that there are some vias that are connected here. So it's useful to specify when your layer is routed on one layer, and then it connects up to the other layer, either above or below, and then continues routing from there. So again, LEF is a very verbose format, and you can search for more examples and more definitions in the LEF-DEF reference manual. The NAND 45 full LEF files are also available online. There's one for the technology and then one for the macros or the masters for this. So you can go ahead and look those up if you want to see more details, including all of the things that were left out. So that wraps up most of the important information about what's stored in LEF, DEF, and Liberty. Do note that Liberty is going to be used for your logical, timing, and power information. And then LEF is going to be used for the physical geometry and routing rules for masters as well as the general technology of the process. And then DEF is going to be your design information. It's specifically for the placement and connectivity of a circuit. DEF is actually a complete superset of Verilog, at least in terms of the defining what are all of the circuit connections. So you can reconstruct your netlist, your graph that represents how is the circuit connected, all from this file. And so these formats are going to make up the basis of OpenRoads databases and will be the subject of future lectures. That's all for this lecture. I'd like to take a moment to thank Nordtech, who provide the funding to make this mini course possible, and I'd like to thank you for taking the time to watch it. I'll see you next time.